In Chapter 9, we're going to talk really just about a small portion of the chapter that has to do with temperature effects. And for some of this, we already know a little bit about this. I mean, those of us that have taken surveying before know that when we are taping in one of our first outdoor lab exercises, that there is a correction factor that we have to apply to the steel tape depending upon the temperature the tape was standardized at and the temperature that we are actually using the tape at. So the logic goes something like this. Even though the tape is 100 feet long, it says it's 100 feet long, that's at a certain temperature. And if the temperature is much warmer outside, that 100-foot long tape will actually be measuring 100 feet, but it's actually more than 100 feet because the tape is actually expanded. So we have to go through a correction process to account for this and actually come up with the real measurement between 2 points. But basically we know that as the temperature goes up, most materials expand, and as the temperature goes down, most materials contract. Again, on smaller type structures, this generally might not be that big of a deal, but we see really examples of this every day throughout our world of civil engineering and construction and structures. I mean, when we look at a bridge overpass that we might drive across, at the beginning and the end of those overpasses, there's an expansion joint. These expansion joints might be very elaborate, or these expansion joints might be very basic, but there is a joint there, as well as possibly joints on the bridge at certain points. But these joints are to allow movement. Okay? So as the bridge gets hotter, it will want to expand, and these joints will want to come together. As it gets colder out, the bridge will want to contract, and these joints will again separate more. But there has to be joints there, because if there's not joints there, then the bridge or the structure or the element or whatever we're talking about would start to build up stress. In this, one of the most basic things that you need to learn is that materials also have a property, a material property, that's known as the coefficient of thermal expansion. And in your book, you can find a table that will list the typical values, the typical coefficients for various common materials for this coefficient of thermal expansion. For steel, for instance, it's typically taken as 6.5 times 10 to the negative 6th inches per inch per degree Fahrenheit. Or if you just expressed it in decimal terms, it'd be 0.5065 inches per inch per degree Fahrenheit. Now, I want you to think for a minute what that really means. Inches per inch per degree Fahrenheit. What that value is, even though it's a very small number, is the strain that's caused by a temperature change of 1 degree. So 0.5065 inches per every inch per every degree temperature rise or fall. Okay? That number's not real big, but again, it's only talking about inches per unit inch. Okay? Now our bridges and things that we utilize every day out there in the world as far as construction is concerned aren't typically 1 inch long. I mean, you could go, over a bridge, maybe across the big river or the Ohio River, and those bridges between piers might be 1,000, might be 1,200, might be 1,400 feet long. 1,400 feet long. Okay? How many inches is that? Well, that's a lot of inches. You can do the math, but when you start taking that small number, and it's not just applied to 1 inch, but it's applied to 10,000 inches or 17,000 inches or 20,000 inches, all of a sudden that deformation that could occur due to that strain is pretty significant. Okay? So again, these values of the thermal coefficient are going to be relatively small values, but when they're applied to real structures, they become relatively significant. Probably one of the most important items with, expansion and contraction of materials and bridges and elements and whatever else we're dealing with is the ability to predict how much a element, a bridge, whatever we're talking about, will deform. And in this case, there's one very basic formula, and it's deformation is equal to alpha, that's the coefficient of thermal expansion, times delta T, that's change in temperature, times L, length. And that's the original length of the member or the bridge or whatever we're talking about. So again, deformation caused by temperature is equal to alpha delta T times L. Those of you that did taping corrections in surveying already, you'll remember that formula. You should remember that formula because that's how you did the taping corrections. Let's do a little example here. We're talking about steel tapes and surveying. Let's say my steel tape measured 100.00 feet. But what happens to that when that tape that measures exactly 100.00 feet, what happens to it when the temperature goes up 50 degrees? Now the thermal coefficient for steel, like we said, is 0.5065 inches per inch per degree Fahrenheit. That deformation formula for temperature that we just saw on the earlier slide would say take the alpha, multiply it by the temperature change, 50 degrees, multiply it by the original length. Now you'll see here I'm expressing the original length in inches. Just the reason I do that is it's probably more typical to talk about deformation occurring in inches than it is in feet. But when I take that, I come out with an answer of 0.39 inches. So that steel tape that was exactly 100 feet long, when the temperature rises, it's actually 100 feet plus 0.39 inches in length. Okay, even though it still says it's 100 feet long. Okay? Now, what's the one other thing that we should recognize? Well, the other thing that we should recognize is that, in our civil construction, architectural elements that we design for and we work with, these are elements that are typically allowed to move, or at least we'd appreciate them more if they were allowed to move. If they're not allowed to move, what's going to happen is that they will build up stresses, and that can have very bad consequences for us. Every once in a while, even around here, it can be July or August, and you'll hear about a road or a highway that buckles, when it gets up to 100 degrees on an August afternoon. Why does that happen? Well, that happens because even a road or a highway is supposed to be built such that it has joints. And if those joints fail for some reason or become inactive, they will not allow movement, and therefore that piece of roadway wants to get longer, but the joints won't allow freedom of movement. And what that causes is stresses to build up in that roadway. And it could be anything. It could be in a building, it could be in a slab, it could be, it could be in anything. All right? So there is one formula that I'll show you down here at the bottom of the slide, but I will warn you that this is a formula that applies to the stress that builds up due to temperature change but it's only good for one material when you have like a concrete slab. Okay, if you start getting members that are made up of two materials, it's not that good anymore. It can't be used directly. The reason that this is good is that if you remember back to the modulus of elasticity, we said it was stress divided by strain. So when I was talking about axial deformation, stress divided by strain, I could have rearranged that formula and said stress is equal to the axial strain times modulus. Okay? Well, in this formula, what this is saying is stress times temperature strain times modulus. So this formula is only good when the temperature strain, alpha delta T, is equal to the axial strain. And that only occurs when you deal with members of one material. So you can use this to calculate stress in a restrained object, but you have to be careful because the only time you can use it is when you have a member made up of one material. Okay, so again, it's a good formula to use, but you have to use it only when you have a one material member or your strain, your axial strain is exactly equal to your temperature strain.